Hi guys. So now we'll be move on to the leading edge devices. So what is the location of the leading edge devices? So as the name suggested, it is located at the leading edge of the wing. So now we will go to the purpose of the leading edge devices. So the purpose of leading edge devices is to increase velocity of the airflow over the top surface of the aerofoil. This results in the transition of turbulence being delayed, and the transition point is caused to move back towards at the trailing edge, and this resulted in an increase in angle of attack and thus increase of lift. So as you can see from the photo there, the leading edge is located at the front of the wing. So there are several types of leading edge devices. So now we'll be focusing on the types of the leading edge devices. So there is four. There are the slots, slats, flaps, and cuff. So first we'll go to slots. So what is a slot? It is a fixed device located in the leading edge of the wing ahead of the aileron. It directs airflow from high pressure area below the wing to the low pressure area at the upper surface wing surface at high angle of attack. It also consequently, it will delay airflow separation until an exceptionally high angle of attack is reached. Moreover, it will maintain aileron effectiveness if located ahead of the aileron and therefore lateral control throughout the stall. However, the slots does not increase the wing chamber, but it allows the wing to achieve a higher angle of attack and thus lift up to the 40%. However, in aerodynamics, everything comes with penalty. So in the slots case, it is drag. It will cap your airplane cruise speed and efficiency. This is because the slots are always open. So this is an example of the airflow of a slotted wing. Okay, so now we'll move on to the slats. The first type of slats is a fixed slat. It has a similar function to slots. It leads additional air from the lower surface of the wing through a gap onto the upper surface of the wing at high angle of attack. Like slot just now, it can only increase the lift up to 40%, but slats it can increase up to 50% and the stalling angle to 20 degrees. Next is the movable slats. It is usually used while landing or performing maneuvers which take the aircraft close to the stall. It is usually retracted in normal flight to minimize drag. The movable slats can increase the lift up to 60% with an increase of angle of attack to about 22 degrees. So it is usually used together with the trailing edge flaps. The lift can be further increased up to 120% and stalling angle to around 30 degrees. And next we will move on to the leading edge flaps. So the first type is the Kruger flaps. The location of the Kruger flaps is between the fuselage and the inboard engine. It is hinged forward of the wing leading edge to increase the chamber of the wing and also increase the wing area needed for high lift at slow speed. It can increase lift by about 50% with an increase in the stalling angle to 25 degrees. So as you can see from the picture, how the Kruger flap is being retracted and extended. Next type of flaps is the variable chamber leading edge flaps. Usually it is used in Boeing 747. Its location is between the inboard engine and the wingtips. It provides the added chamber needed to produce high lift at low speed. It is usually made from flexible composite material. The flap have a curved outer surface which changes the wing contour when extended. It also forms a slot to function as a movable slats. So now we will go to the short video on how the variable leading edge flaps works. So this is the extension of the variable leading edge flap. As you can see, it increased the wing chamber and now it is being retracted. So that is how the variable chamber leading edge flap works. And next, lastly, is a curved leading edge. It is a fixed aerodynamic wing device employed on a fixed wing aircraft to improve the stall and spin characteristics. It is usually a lightly drooped outboard leading edge. Extension starts about 50 to 70% half span of the outer leading edge of the wing. This is to produce a more gradual and gentler stall onset without any spin departure tendency. The further benefit of curved leading edge is to lower the stall speed with lower approach speeds, shorter landing distances, and improve aileron control at low speeds. So that is all from me. So
Hello, today I'll be talking about trailing edge devices. Most common device is the trailing edge flap for the trailing edge devices. These trailing edge flaps are attached to the trailing edge of the wing for the purpose of increasing the lift of the wing at a particular speed and angle of attack, and also to increase the drag. Trailing edge flaps are useful during the approach for landing to increase the gliding angle and to decrease the landing speed of an aircraft. Retracted to be streamlined with the wing to produce a minimum of drag during cruising flight. Trailing edge flaps can also be used for takeoff as well. There are several types of trailing edge flaps. So the first type is flame flap, which is also known as chamber flap. Plane flap increases the aerofoil chamber, resulting in a significant increase in the coefficient of lift at a given angle of attack. If it is lowered fully, it greatly increases drag and moves the center of pressure aft of the airfoil, resulting in a nose-down pitching moment. Normally, plane flap is used on small aircraft, and the flap can provide 50% increase in lift. The second type of the trailing edge flap is the split flap. The split flap, it is deflected from the lower surface of the airfoil, which produce about 60% increase in lift, which is slightly greatly than the plane flap. When it is fully extended, it will produce high drag with little additional lift. More drag is created with split flap because of the turbulent air pattern produced behind the airfoil. The third type of trailing edge flap is the slotted flap, which is most popular flap on the aircraft these days. And slotted flap increases the lift coefficient significantly more than plane or split flaps. And the hinge is located below the lower surface of the flap. When the flap is lowered, a duct or slot forms between the flap well in the wing and the landing edge of the flap. So high energy air from the lower surface is ducted to the flap's upper surface through the slot and accelerates to the upper surface boundary layer and delays airflow separation, which provides a higher lift coefficient. And slotted flap produces much greater increase in lift up to about 60%. Last but not least, Fowler flap. a type of a slotted flap, and Fowler flap is not only changes the chamber of the wing, it also increases the wing area. Instead of rotating down on a hinge, it slides backwards on track. First portion of its extension increases more lift than drag. Last portion of the travel increases more drag than lift, which causes a large rearward movement of a center of pressure. Fowler flap with a single slotted can increase lift up to 90%, while double can increase lift up to 100% and stalling angle to 20 degrees.
So we move on to the next secondary flight control devices, which is drag-inducing augmentation devices. So the purpose of the devices, these devices is to reduce the speed or lift of the aircraft in order to achieve and assist in a required flight condition, such as maneuvering, gliding, descending, and landing. So it is also called a spoiler. It is small hinge flat panels on top of portion of wings forward of the trailing edge flaps. It is operated hydraulically in the flight or ground mode. And it's generally classified as flight spoilers, ground spoilers, or lift dampers. So it is the type of spoilers. As you can see here, this is the flight spoilers or roll spoilers. This is the ground spoilers. Here. Right. So first we have flight spoilers. So it is used in conjunction with the aileron and gives more improved lateral control. It is deployed within certain airspeed range when the outgoing aileron moves past the certain angle. So as you can see here, this is the outgoing aileron. So at certain angle of this aileron being deployed, this set of flight spoilers also will be deployed, and it is automatically extended to reduce some of the lift and produce more drag, which is assist to the roll of that desired direction. So why the spoilers contribute in rolling the aircraft? It is because the spoilers help to eliminate adverse yaw produced by downgoing aileron. So as you can see, when your adverse yaw happen when this side produce more drag, this wing produce more drag than the outgoing aileron, then this side of the wing. So the aircraft go to that side, yaw to the side. So the spoilers is help by increasing the drag and eliminate the yaw, the adverse yaw. So the spoilers on the wing with downgoing aileron remain flush with the surface of the wing. So this is the downgoing aileron. So as you can see, the spoilers is flush. So lastly, we have ground spoilers or lift dampers. So both the flight spoiler and ground spoilers on both wings automatically rise to their maximum angle on touchdown. Aircraft wheels rotating provide time delay and ensures the aircraft is on the ground. There are certain conditions where this ground spoiler can be deployed. First, take brake lever in the arm position. As you can see, the arm position is not one of the angle of the spoilers. It is used during touchdown. So initially, the pilot must pull the lever to the arm position before touchdown, upon landing. An aircraft weight on the undercarriage ground sensing system. So there are sense device on the landing gear. So when the aircraft touch down, the sense will trigger, sensing device will trigger, and all thrust levers in the ideal position. When the aircraft touch down, actuator automatically move the split brake lever to the up position. So when the sensing device is triggered, this lever will automatically pull, not being pulled by the pilot, but automatically pulled by the system to the up position, which is the maximum angle for the spoilers, for both spoilers, flight and ground spoilers. And with fully raised, the lift is reduced by approximately 80%. The aerodynamic drag more than doubles. The loss of P puts the aircraft weight on the anti-carriage, and this will increase the directional control, improve braking, and reduce the risk of aquaplaning on wet runways. So after landing, after the aircraft fully stopped, the brake lever automatically moves down position to rotate the spoiler. So when the aircraft is fully stopped, and fully stopped and taxiing, the lever will automatically push by the system to the down position, which is when the spoilers are fully retracted. Yeah. So that's all for me. We will move on to the next secondary flight control system. Thank you.
From now on, I will continue the presentation on trim system, specifically trim tabs. So what are trim tabs? They are secondary flight control surface that help you reduce or eliminate the need to place pressure on the yoke, or rather to keep your airplane flying straight and level. So there are four main types of trim tab. Number one is trim tab, balance tab, anti-servo tabs, and last one is ground adjustable tabs. So now that you know the four types of trim tabs, so let's take a look on how each one of them work. So let's take a look at the first one is balance tab. Some aircraft have a very heavy control load, especially at high speeds. That's where balance tab come in handy. Balance tab look like trim tab, but they have one major difference. Balance tab are attached to the control surface linkage, where the control surface is moved in one direction and the balance tab move in the opposite direction. By moving the balance tab in opposite direction, the control load on your yoke is significantly reduced and making your airplane easy to fly. Trim tab. The trim tab is attached to the trailing edge of the elevator, and it's operated by moving a small control wheel in the cockpit. Roll the wheel in the nose up position and the tab moves down. Roll the wheel in nose down position, the tab moves up. When you move the trim tab up or down, it sticks out into the free air strip and deflects the elevator in the opposite direction. So even though it may seem backward to move the tab down to make the nose of the plane go up, seeing the tab in action helps. It all makes sense. Anti-servo tab. Anti-servo tabs are similar to balance tab, but they move in the opposite direction. For example, when your elevator or stabilizer moves up, the anti-servo tab moves the same direction. Small aircraft increases the control field and helps prevent you from over-controlling your aircraft's pitch. One of the most popular examples of anti-servo tab is on Piper Cherokee. Without it, the plane would be much easier to pitch up and down, but it would be also easy to over control and possibly overstretch the airframe. So the last one is ground adjustable tab. Ground adjustable tab are just that only adjustable on the ground, as the name is already described what it is. So how do you adjust? By bending it left or right, preferably between two solid surfaces like blocks of wood. The ground tab is used to keep your plane flying coordinated in level flight. And since it's a try and error system, it might take a few flights of adjusting, flying, and more adjusting. But once you get it set, you are good.
Anti-balance tab. Link in such a manner that the movement of the tab is in the same direction as the primary control surface but further. Used on large flight control surface such as stabilizer, and it can be found on F-86 aircraft. and it makes the control more effective, and to give the pilot more feel when moving the control. Forced work. It used to reduce the effort required to move the control. Same working principle as the movable trim tab, with the only difference it is operated by the primary controls. The primary control moves the tab to develop aerodynamic force, which in turn moves the primary flight control surface. And it works very well at reasonable high speed, but produces poor control surface response when at low speed. For spring tab, it is a small auxiliary tab set at the trailing edge of a primary control surface of a high-speed aircraft. Tab's movement is controlled by the primary control system. At normal or low-speed flight, the tab moves together with the primary control surface due to insufficient aerodynamic load. While at high speed, the aerodynamic load is high enough to overcome the spring pressure for control rod to move the tab. The tab moves in opposite direction to the primary control surface. Now for adjustable stabilizer, it is the alternative to elevator trim tab. The horizontal stabilizer linkages is pivot about its rear spar, as you can see on the figure on the right hand side. It uses jack screw that is mounted at the leading edge of the stabilizer and controllable from the flight deck. On small aircraft, the jack screw is cable operated, mechanically using trim wheel or crank. On the bottom figure, just below the jack screw figure just now. And for larger aircraft, the jack screw is electrically motor driven. It can be controlled manually and automatically, which is manually using control wheel by the pilot, where they're usually adjusted before the takeoff, depends on the aircraft loading, and autopilot using pitch control computer when they get the input from the phase of flight. And the trimming effect is similar to those of the trim tab. Adjustable stabilizer, or as known as variable incidence stabilizer or trimmable horizontal stabilizer (THS). It is an instinctive switch in the flight deck enables the pilot to increase or decrease the tailplane incidence. Long-term nose or tail heaviness can be trimmed by altering the incidence of the variable incidence tailplane of stabilizer, and it allows the elevator to remain streamlined with the stabilizer, and its full range of travel is available for control. There are two conditions that are capable of producing the same amount of stabilizer's lift. As you can see, the first one is upward lift, the A figure on the right hand side. Stabilizer at 0 degree with elevator down 10 degree, or just below that, stabilizer at only 3 degree while elevator faired. They produce the same amount of lift. And for downward force, figure B on the right hand side on the bottom, stabilizer at 0 degree with elevator up 15 degree, or stabilizer at -6 degree and the elevator is faired. Although the lift is the same in each case, the drag is less when the elevator is faired or streamlined. And in addition, elevator full range of travel for control is available.